Allow me to introduce myself. My name is Arif Nugroho. You can call me Arif. I'm from Department of Electrical Engineering, Institut Teknologi 10 November. In this occasion, I want to tell you about my research paper with the title Accelerometer Calibration Method based on the polynomial curve fitting with the author Arif Nugroho, Agustinus Bimo Gumelar, Eko Mulyanto Yuniarno, and Mauridi Heri Purnomo. This is the table of the content. The first is the introduction, and the second, the problem statement, and the third is the objective of this research. And then we explain about the accelerometer sensor, and then we propose the accelerometer calibration method based on the polynomial curve fitting. And the last section, we provide the conclusion. Accelerometer sensor is a microelectromechanical system that can be applied for measuring the motion state of the object. So, most of the applications regarding the motion control frequently use the accelerometer sensor. It can be proved from the multiple applications, such as the autonomous flight stabilization in drone, self-balancing robot in a humanoid robot, and smartphone navigation system. On the other hand, we can use the accelerometer sensor for the marine vessel in order to stabilize the marine vessel from the wave obstacles. This is the problem statement of this research. The first, the calibration process is a fundamental step that should be conducted before going to the measurement process. Second, the use of the accelerometer as the measurement tool must be reliable and valid in expressing the values. And the third, it is required the accelerometer calibration method that can guarantee the reliability and the validity of the measurement result. This is the objective of this research. The first, we propose the accelerometer calibration method based on the polynomial curve fitting. And the second, we propose this accelerometer calibration method to guarantee the reliability and the validity of the measurement result. And the third, to guarantee the reliability and validity of the accelerometer sensor in expressing the values. Accelerometer sensor is a microelectromechanical system that can be applied for measuring the motion state of certain object. By using the motion state of certain object, such that we denote in the tilt of the accelerometer, the elevation, or inclination, or vibration, we can use this accelerometer for several applications. In this research, we use the accelerometer with the type MMA 7260, in which it can be only accessed by using the analog to digital converter channel. On the other hand, we can find the accelerometer that work based on the I2C channel. But in this research, we just focus on the accelerometer sensor that works based on the analog to digital converter channel. By using the analog to digital converter channel in a microcontroller, the tilt of the accelerometer sensor with the degree unit will be converted into the corresponding voltage. In this case, the tilt of the accelerometer sensor is the analog signal, and the accelerometer voltage is the digital signal. From the block diagram that we provide in this slide, we can see that the microcontroller will read the tilt of the accelerometer from the accelerometer state, and by using the analog to digital converter, a microcontroller will convert the tilt of the accelerometer sensor into the voltage. And then the data that contain the tilt of the accelerometer and the corresponding voltage will be visualized through the monitor. The accelerometer with the type MMA 7260 consists of a triple axis X, Y, and Z, where all of the axes have the same input-output value as shown in figure. From this figure, we can see that all of the axes have the same input-output, both in the tilt of the accelerometer sensor that we denote with D and the corresponding voltage that we denote with the V. This accelerometer sensor works based on the analog to digital converter, where it converts the tilt of the accelerometer sensor into the corresponding voltage. However, from the data acquisition, we only have a set of the accelerometer data without knowing the mathematical model that relates the tilt of the accelerometer sensor into the corresponding voltage. It is very important to find the mathematical model, because by using this mathematical model, we can calibrate the accelerometer correctly. From the data acquisition, we have 1025 data points. By using this data, we can generate the mathematical model based on the polynomial curve fitting. Before applying the accelerometer sensor to measure the motion state of certain object, the accelerometer sensor should be calibrated correctly. It is intended to guarantee the reliability and the validity of the accelerometer sensor. Reliability refers to the consistency of the measurement result, and the validity is about the accuracy of the measurement result. In this research, we proposed the accelerometer calibration method based on the polynomial curve fitting with the 5-order polynomial. We mentioned it with the 5-order polynomial because the highest power in this equation is 5. In the previous section, we emphasized that this accelerometer consists of triple axes such as X, Y, Z. Firstly, for the x-axis of the accelerometer, we construct the objective function based on the 5-order polynomial. This equation is defined in the matrix form, where theta x are the tilt of the accelerometer sensor, Vx are the voltage of the accelerometer sensor, and C are the set of the coefficient. This equation is constructed from the 5-order polynomial that we provide in the previous slide. The goal of the proposed calibration method by using the polynomial is how to find the set of the coefficient that can map each of the voltage value into the tilt of the accelerometer sensor correctly. Based on the data acquisition, we have the data that contain the tilt of the accelerometer that we denote with the theta, and we have the data that contain the voltage that we denote with the V. But in this equation, we don't have the set of the equation, the set of the coefficient that represent for the C1, C2, C3, C4, C5, and C6. Therefore, to get the appropriate coefficient, we use the pseudo-inverse technique. By using this technique, we can extract for obtaining the set of the coefficient. By using the pseudo-inverse technique, we obtain the set of coefficient for each variable. Namely, C1 is equal to 117.84. C2 is equal to minus 972.24. C3 is equal to 3175.84. C4 is equal to minus 5132.75. C5 is equal to 1178.15, and the C6 is equal to minus 1421.34. Therefore, we can construct a mathematical model that relates a number of the voltage value into the tilt of the accelerometer. By plugging the set of the coefficient that we obtain, we can generate the mathematical model for calibrating the accelerometer sensor. So we can see in this slide that we get the mathematical model by substituting the voltage in the data acquisition into the mathematical model. We can generate a number of degree by plotting the prediction data that we obtained from the mathematical model. We can see that the target data and the prediction data is fit to each other. For the y-axis of the accelerometer, we construct the objective function based on the 5-ordered polynomial. This equation is defined in the matrix form, where theta y are the tilt of the accelerometer sensor, Vy are the voltage of the accelerometer sensor, and C are the set of the coefficient. The goal of the proposed calibration method by using the polynomial is how to find the set of the coefficient that can map each of the voltage value into the tilt of the accelerometer sensor correctly. To obtain the appropriate coefficient, we use the pseudo-inverse technique. By using the pseudo-inverse technique, we can obtain the set of the coefficient where all of the set of the coefficient is the same to each other between the axis starting from the x, y, and z. Therefore, we can construct a mathematical model for the y-axis of the accelerometer. By comparing the target and the prediction data, we can find out that our proposed calibration method has been successfully applied for calibrating the accelerometer sensor. For the z-axis of the accelerometer, we construct the objective function based on the 5-ordered polynomial. This equation is defined in the matrix form, where theta z are the tilt of the accelerometer sensor, Vz are the voltage of the accelerometer sensor, and C are the set of the coefficient. This equation is constructed from the 5-ordered polynomial that we defined in the previous slide. The goal of the proposed calibration method by using the polynomial is how to find the set of the coefficient that can map each of the voltage values into the tilt of the accelerometer sensor correctly. To get the appropriate coefficient, we use the pseudo-inverse technique. Pseudo-inverse techniques we use to extract the set of the coefficient from the objective function. By using the pseudo-inverse technique, we obtain the set of the coefficient. And then we can construct a mathematical model that relates a number of voltage values into the tilt of the accelerometer. By substituting the voltage value into the mathematical model, we can predict the value of the tilt of the accelerometer. By comparing the data from the target and the prediction data, we can see that our proposed calibration method has been successfully applied for calibrating the accelerometer. For the conclusion, based on the experimental result, the proposed calibration method based on the polynomial curve fitting has been successfully applied for calibrating the accelerometer, with the mean absolute error score is 0.57. The calibration process in the measurement tool, such as the accelerometer sensor, must be conducted before going to the measurement process. It is intended to guarantee the reliability and the validity of the measurement result. The calibration process of the accelerometer sensor is the fundamental step that must be fulfilled because it is the prerequisite of the measurement process. That's all from me. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.